Hello students, welcome back. In the previous section, we talked about homogeneous versus non-homogeneous equations. We talked about the terminologies, definitions, some examples, including some tedious computations. We also talked about the fundamental theorem as well, and the existence and uniqueness of linear ODEs. Uniqueness is particularly important, which means no matter what method we use, if you have a solution, that is the solution. Anyway, let us now move on to the second section, and this too is the kind of preparatory step. Let's talk about the linear independence and linear dependence. Functions y1, y2, all the way to yn are said to be linearly independent. Real functions y1 through yn are said to be linearly independent if c1y1 plus c2y2 plus c3y3 all the way up to cn yn is constantly equal to 0, means all the coefficients are 0. That's what linear independence means. Likewise, real functions y1 through yn are said to be linearly dependent if there exists n tuple of real numbers c1 through cn, not all of them 0, such that c1y1 plus c2y2 all the way up to cn yn are constantly 0. That's the definition of linear dependence. As a matter of fact, you can easily check. One is the negation of the other, as a matter of fact. And if you have n tuple of real functions, it's going to be either, that n tuple is going to be either linearly independent family or linearly dependent family. It's basically whether you can find out coefficients that are not all 0, yet linear combination c1y1 plus c2y2 all the way to cn yn is constantly equal to 0. If that's possible, then linearly dependent. If that's impossible, then linearly independent. By the way, this expression here, c1y1 plus c2y2 plus ... cn yn is called a linear combination. A linear combination. So using the term linear combination, I can read these definitions a little bit more smoothly. Let's go again. Real functions y1 through yn are said to be linearly independent if the linear combination is constantly 0, implies all the coefficients are 0. Also, real functions y1 through yn are said to be linearly dependent if it is possible to find coefficients c1 through cn, not all of them equal to 0, yet the linear combination is constantly 0. In that case, we linear dependence. And let me emphasize again, the key is to find out these coefficients that are not all of them 0. If that's possible, linear dependence. If that's impossible, linear independence. A little bit hazy? Let's solidify our understanding through a couple of examples here. We have these four functions. y0 is 1, y1 is t, y2 is t squared, y3 is t cubed, and let's check the linear dependence or independence. It'll turn out to be that these four functions are linearly independent. Let's begin with a linear combination constantly equal to 0, which means equal to 0 for all t. For all t. For all t, so let's select some easy t values. We have 4 constants, c0, c1, c2, c3, so we need 4 equations. Let's select 4 t values, t equal to 0, 1, negative 1, and 2, and put those in. And then we're going to get the system of these 4 equations. Plug in 0, then we're going to get all 0 here, so we get c0 equal to 0. Plug in 1, then t to whatever power is all 1, so we have c0 plus c1 plus c2 plus c3 equal to 0. t is -1, we have plus minus plus minus. T is 2, then you're going to get 0, 2, 4, and 8, like these. Solve the system of linear equations, you're going to get all zeros. It's easy. What if you select some other t values? Other than these, some difficult t values. Am I going to get zeros too? Yes, you will. Yes, you will. But why would anybody bother? I cannot guess. It's much easier to select easy as possible t values, right? Here's our next example. We have these three functions, and are they linearly independent or dependent? It'll turn out they're linearly dependent. Why? Because it is possible to get appropriate linear combination which is constantly equal to 0. If you select coefficient 1, 1, and the -1, and we get constantly equal to 0, please note that t minus t cancel each other out, and then also constants cancel each other out. So if it is possible to find out those coefficients, then linearly dependent. Impossible, then linearly independent. Now, next topic we have to talk about is Wronskian determinant, and a forewarning. I don't emphasize this very much, even though our textbook author emphasizes it a lot. As a matter of fact, every single differential equation textbook I've ever seen emphasizes this Wronskian determinant a lot. I don't. Let's talk about it. A family of differentiable functions y1 through yn are linearly independent if the determinant of a certain matrix is non-zero. And what's that determinant? First function y1, and we simply take the derivative all the way to the column. First derivative, second derivative, all the way to n minus first derivative. And second function y2, y2 prime, y2 double prime, all the way to nth derivative. And then the last function yn, first derivative, second derivative, third derivative, all the way to n minus first derivative. Get all those columns. And then we get n by n matrix. Calculate this determinant. If the determinant is 0, then we have linear dependence. If the determinant is non-zero, then we have linear independence. And let's check that with appropriate example, and the same as the previous example. 1 t squared t cubed. And then let's set up Wronskian determinant. Start from 1 and take the derivatives. Derivative is 0, so we have 1, 0, 0, 0. Next, start with t and take the derivative. That's 1, and next derivative is 0, so we get that. Next, start with t squared and then take the derivative. Derivative, we get this column. Finally, start with t cubed and then t cubed, derivative, you get this column. What is the determinant? If you calculate it correctly, you're going to get 12. That's not 0, so we have to have linear independence. By the way, how do I calculate this so quickly? Because this is a triangular matrix, everything down here is 0. So the determinant is just product of the principal diagonals, just 1 times 1 times 2 times 6. This is not the general formula of this determinant's computation. It works in this particular case. How about the next example here? Well, we can calculate Wronskian determinant similarly. First function, derivative. Second function, derivative. Third function, derivative, another derivative, first and second derivative, and calculate the determinant. It'll turn out to be 0. Again, this is triangular matrix, so you can simply multiply the diagonal, but this is not always the case, so let me remove that. So we have independence and dependence using Wronskian determinant. But then again, I already said I don't like this one very much. The title of this chapter is Second Order Linear Differential Equations. For second order, there is much easier method. Let's talk about that. We have two real functions, y1 and y2, and they are linearly dependent if and only if one is constant times the other. Either y2 is c times y1 or y1 is c times y2. We say y1 and y2 are collinear if neither is a zero function. So y2 is something times y1, so y1 is 1 over that something times y2. Consequently, that c has to be non-zero. You see, y1 and y2 are both non-zero, then c cannot be 0. What if c is 0? In that case, y2 will be 0. What if this c is equal to 0? Then y1 will be 0. Either way, we'll have to have linear dependence. How to prove this? Let's do the proof and then let's work out some examples. Okay, let's prove it. One direction. Suppose that we have linear dependence. Then can we express as one is constant times the other? Yes, you can. What do you mean by linear dependence? It is possible to find out c1 and c2, not all of them 0, so that c1y1 plus c2y2 is constantly equal to 0. Not both of them are 0. You see, if c1 and c2 both of them are 0, in that case we have linear independence. So one of them is non-zero. What if c1 is non-zero? Just divide by c1. Just divide by c1 and then solve for y2. Excuse me. Divide by c1 and solve for y1. So excuse me, it should be this. y1 is c2 over c1 times y2. Okay. So yes, it falls into this category. What if c2 is non-zero? Then divide by c2. Then y2 is negative c1 over c2 times y1. Yeah, okay. It'll fall into this category. So yes, if you have linear dependence, then it's going to be either A or B. So it works out. One function must be a constant times the other. Now let's prove the other direction. Okay, let's assume this one. One function is constant times the other. What if c equal to 0? If c equal to 0, then if this is equal to 0 and this function is 0, and if that's equal to 0 and that function is 0, so if you have c equal to 0, then we have to have at least one 0 function. In that case, we have to have linear dependence. What if y1 is constantly 0? Then this is 0. So kill off the other by 0 times, and then get any number here. 1 is the simplest. Then we have constantly 0. So we found c1 and c2, which are not all 0, but constantly 0 in the end. What if y2 is 0? Then kill off y1 by multiplying by 0. And then what do you have? 1 times y2 is constantly 0, so we have 0 function. So what did you get? Not both constants are 0. Not both constants are 0, but the linear combination is equal to 0. We got that. Now what if c is non-zero? Either here or there. That's even easier. Just flip the other side. Then you're going to get coefficient y1 plus 1 times y2 is constantly equal to 0. We get that. Or 1 times y1 plus negative this coefficient y2 is equal to 0 constantly. So what do you get? We have linear dependence either way. So the conclusion, if you have collinearity, one function is constant times the other, then you're going to get linear dependence. It's a lot easier than Wronskian determinant. Let's check it out using a couple of examples. Here we go. I selected cosine and sine function. All right. Check for linear dependence or independence. Is one function constant times the other? Let's take the ratio. y2 over y1 is sine over cosine, and its tangent is not constant, which means this is not collinear, so linear dependence. Can you check it out with Wronskian? If you want to, yes you can. Start from cosine and take the derivative, we have this column. Cosine and its derivative. Start from sine and take the derivative, we have this column. And then calculate the determinant, you're going to get this computation, not zero, so linear independence. Same conclusion as before, but harder computation. How about the next example? Dependent or independent? Let's check the collinearity. Is one function constant times the other? Let's take the ratio. y2 over y1 is t, it's not constant. So not collinear, not independent, so linear dependent. Now what about Wronskian determinant? Start from exponential of 3t, take the derivative, we get first column. Start from here, take the derivative, we get the second column using the product rule and chain rule. Already there is a red flag. And then let's go ahead with determinant computation. And then some further simplification, and we have exponential of 60. Exponential is never equal to 0, so all looks good. So we have correct computation, correct conclusion. However, do we prefer this computation or this computation? I don't know about you, but in my experience, every single person preferred to check collinearity rather than Wronskian determinant. I certainly did it when I was a student, and I have never seen anybody else who'd prefer to do it this way, except for textbook authors. And I can understand their reasoning, yes, because Wronskian determinant is necessary for higher order differential equations, and also Wronskian determinant itself is an important topic in differential equations. So yes, I can understand that. But for our purpose, and particularly we are doing second order linear differential equation, and I'm not going to emphasize it. If you're not check linear independent dependence, check for collinearity. See if one function is constant times the other. Yes or no? We have dependence, yes. Independence, no.